Okay, let's start. It's my pleasure to introduce today's speaker, Yanbo Chen. And Yanbo holds a bachelor degree in computer science from Fudan University. He's now a third-year PhD student at the University of Ottawa. Interestingly, Yanbo had been here like for his first PhD semester here at CUHK, and that's like before he moved to University of Ottawa with Professor Andrei Bogdanov. He's like generally interested in cryptography. His recent research focuses on like threshold signatures. Today he's going to share with us his new progress and thoughts on the adaptive security of threshold signatures. Yeah, let's give him applause. With that, the stage is yours.
Thanks for the introduction and thank you all coming. So my title is Recent Advances in Adaptively Secure Special Signature, but I need to narrow down a bit the title. Actually, the recent advances only occur for some type of signatures, BLS Schnorr and the friends of Schnorr. What's common in this signature scheme is that they all have very simple special protocol. Okay, yes. Oh, great. Okay, let me begin with some background. Digital signature is a textbook crypto primitive. In a signature scheme, we have three algorithms. The key generation algorithm generates a secret key and a public key. Using the secret key, the signing algorithm can generate a signature sigma over a message mu, such that anyone can verify the signature using the public key. The security requirements of signature scheme consider an adversary who knows the public key but doesn't know the secret key. It can query signatures, it can query many signatures over messages of its choice. The goal is to forge a signature on a new message. So this security notion is called unforgeability. The idea of special signature is to distribute the ability of signing to multiple users. Here, the secret key is distributed among n users by a trusted dealer or a distributed key generation protocol. In this talk, and also in this line of research, we usually assume a trusted dealer. However, in practical, we usually don't want the trusted setup, and we run a DKG protocol. So the way of defining special signature with a trusted dealer somehow separate the signature protocol from the DKG protocol. And it turns out that even if assuming a trusted dealer, we have some interesting things to study. So here we assume a trusted dealer. The secret key is distributed in a way such that any T+1 users can jointly sign, but any T users cannot. So the T is called the threshold. An important component in the definition of special signature is the availability. Usually for crypto primitive, we define correctness. For signature, it means that a signature generated from an honest execution of the protocol should pass the verification. In the distributed setting, we consider availability, which is about the signature generation in presence of malicious users. So special signature is not a new topic, actually. It has researched 30 years ago. The traditional line of research usually requires a strong form of availability called robustness. In this setting, the signature protocol is for all the end users. Robustness requires that the protocol guarantees a signature as long as T+1 honest user participates in the protocol. So here, 5 users participate, 2 of them are malicious. Robustness will guarantee that a valid signature will be generated. So for special Schnorr, in this setting, well, the best thing is that we need to run the distributed key generation for each signature. So for key generation, we run DKG to get a permanent key, the permanent key. However, for each signature, we also need the DKG to generate a one-time key. So this is not that efficient in communication, in run complexity, and so on. The modern line of research, I need to say that the robustness is still important now. So it is still an active area. But in a modern line of research, people think that a weaker sense of availability is enough for some application. It is called identifiable abort. In this setting, the signature protocol is defined for just T+1 users. So if there is one malicious user, then it can let the protocol fails without generating a valid signature. However, IA guarantees that we can catch the malicious user when the protocol fails. This can be combined with some external mechanism, like we can record this malicious behavior and maybe kick it out in the future. In this modern setting, Komlo and Goldberg construct a very efficient special Schnorr, where the user only need to preprocess in one round, and then they are prepared for a one-line online signing protocol. So this work is about the modern line of research. So I said special signature is not a new topic, but in this year it gets renewed attention. No surprise, it's because its applications in blockchain. So I will list 2 of them. First is in digital wallets. In a cryptocurrency system, your money is in a digital wallet associated with a public key. To spend your money, you just sign a transaction. So special signature allows you to distribute the secret key among multiple devices. So every time you want to spend your money, there is something like a multi-factor authentication. Suppose you are using 2 out of 3 special scheme. Then if one of your device is lost, then your money is still secure. Right. The other application is in proof of stake consensus like ETH. In that blockchain system, there is a validator committee. Anytime there is some update to the system, for example, a new block, the committee has a vote. If, say, 6 out of 10 agree with the new block, they can generate a special signature on the new block and send to the whole community. Then the new block becomes the consensus of the community. So there is, of course, a naive solution, that is to let all the validators individually sign the block. So compared to the naive solution using special signature, the community only needs to see one public key and verify one signature. They does not need to see each public key of the validator, also the individual signatures. Great. So I have deferred the security model for special signature until now. There is a model called static model. In this model, the adversary statically corrupts T users. So remember that in a special signature scheme, we want to guarantee that T+1 user can sign, but T users cannot. So we let the adversary to control T users. The adversary first corrupt T users, then the scheme is initiated from the very beginning, from the key generation. Then the adversary can interact with the honest users. This corresponds to the security model for standard signature scheme. The adversary can query signatures. Here we are in an interactive protocol, so the adversary just interact with honest users and get protocol messages from the honest users. Another security model which is important for this talk is called the adaptive model. In this model, the scheme is first initiated and the adversary can start to interact with its honest users. It can adaptively corrupt and interact with the users. For example, it can first interact with every user. Then, based on the transcription, it decides which user to corrupt. Continue the interaction, decide the next user to corrupt, and even continue more. So the adaptive model follows a principle in crypto. We are usually happy to think about a maximal power adversary. And it's actually somehow a standard notion or important notion has been studied in the traditional line of research. There is also a standard setting. We do not assume secure erasure. This means that when the adversary corrupts a party, it does not only see the secret key of the party, it also sees the whole computation history, including the secret randomness. It may not be hard to see that there is a generic reduction between these two models by guessing the T users to be corrupt by the adaptive adversary. So these two models, they are equivalent when the number of users is small. However, when the number of users is like several hundreds, then this loss of n-truth T is not acceptable. So we need to separately study adaptive security. Right. So at the end of the background, I also want to mention an ongoing standardization effort by NIST. So this is another important motivation of this line of research. So now this standardization is still in a draft state. That is, they are still discussing what to write in the standardization call, what to require on the submission. In the proposed timeline, the submission should be in next year. So I want to highlight something about signature in now the draft. So first is about the scope. The most important part is those signature schemes that has been standardized by NIST. Here in this list, we can see EDDSA, ECDSA. These are elliptic curve-based signature. We see an RSA signature, and we see 3 post-quantum scheme. Here I highlight EDDSA, and because basically it's just Schnorr. So what I want to say here is that social Schnorr is in an important place in this standardization. On the other hand, the scope of this standardization is quite wide. So they say that even if a scheme is not standardized by NIST, if you have clear advantage, like more social friendly, more ZKP friendly, something like this, it may be meaningful to specialize it. And last, I want to stress that in this call, adaptive security is highlighted as a standard notion. So this standardization effort is another important motivation of this line of research. So I have I have narrowed down my talk at the very beginning. So after this background, I state it again. This talk is about the recent line of research in special BLS, Schnorr, and friends. They are in the modern non-robust setting. And all of them are efficient and simple. And actually, maybe just because they are so simple that we start to study adaptive security. If we haven't know how to efficiently sign even with statically security, then maybe adaptive security is just a second goal. Okay, now then I will give an overview of the recent work without talking about the technical details. So first is about the BLS signature. BLS signature is a very efficient pairing-based signature scheme. It's so simple and efficient. 2 years later, 2 years after the proposal of BLS, we already have a simple special BLS scheme. At that time, it's only proved in the static model. For adaptive security, we don't know. We don't know approve. We didn't know approve. We didn't know an attack. But people did care about adaptive security. So there was work that proposed new construction, achieving adaptive security, even though it does not give a standard BLS. It's less efficient. It had longer signature. So these are not the recent work. Recently, Bachong and Loss proved that the classical simple BLS is adaptive secure, assuming somehow non-standard assumption, one more disk below OMDL, and an idealized model AGM. I don't want to talk about the technical details, so roughly speaking, this result says that the scheme is secure in an idealized group, where in an idealized group, the attacker can do nothing useful in the bit representation of the group elements. It's like it only see an abstract in the group element, and it can only do group operation on the elements. So this idealized model is clear a research gap. So following, there is a work by Das and Ren, construct new special BLS scheme achieving adaptive security from standard assumption without the idealization.
It's co-CDH.
Co-CDH is some a CDH on pairing group. It's in asymmetric pairing group. Yeah.
That's codomain CDH.
Mm.
Look, I have a question. Let's say I have a static secure backup signature. Is it true that the same construction, if I'm happy to make a super polynomial harness assumption, I can make it I can prove it's adaptive secure?
You can prove it with general reduction with like super polynomial security loss. So
that just means if, for example, if I build a construction from say pairing, it's only static secure. Yeah. But if I'm happy to make super polynomial harness assumption for the underlying like pairing problem, then
I think
it'll be adaptively secure.
I think
basically,
maybe
you need to
not.
make the assumption strong to absorb the super polynomial loss. Yeah, that was.
Well, I personally think it may not, but maybe I didn't understand clearly. So
maybe another term is complexity leveraging.
Yes.
You know complex leveraging, right? Or
I think they can be thought of a complexity leveraging. Yes.
do you know?
I see. So if you want to build your scheme in a large enough group, then you can absorb the super polynomial loss. That's true. Right.
Well, that would have a inefficient
Right. So
right?
so maybe the security law is 2 to the 128, and then if you build on a group with security 500 bits, then it will be okay. But practically, we want the group also have security 128.
I see. Okay. In essence, we were talking about one of the previous constructions. You said we don't know any attack. I think if you are happy with making stronger hard assumption, it's definitely secure.
Yeah,
But it's unlikely that you will find it.
yeah, but this may, in the practical part, this may affect the parameter choice, affect the group you choose.
I see.
I have a question.
Yeah.
Short of NPCs, if I just have a standard signature, is there a generic way to build a threshold signature?
Yes, you can use generic protocol, generic MVC, something like this. Yes.
But nothing below NPC. You kind of need NPC.
As far as I know. Yes.
No. Because the minimum assumption for NPC is OT. But for threshold signature, I'm not sure if public assumptions are necessary. We don't have.
There is a recent work that you can build build upon one function. But you use some.
Then you cannot say
Yes,
that NPC is the minimum
that's true. Yeah. But the idea is related to MVC. We just read.
Yeah, of course,
but,
everything is secret sharing.
Yeah.
So you have threshold signatures from one-way functions.
Yeah. Yes.
Signatures.
Yes.
I'll ask.
Okay. So, the construction of does and run is although a bit less efficient than the classical simple BLS, but it's already efficient, very efficient concretely, and it gives a standard BLS signature. So basically, this line of research is closed, basically. Yeah. And looking back, like if consider we are practitioners, which scheme we want to implement in the real world? Probably just the simple BLS. After seeing the proof, actually, if there is no attack, then practitioner may already be happy to implement it. Given the proof in the idealized model by Bartram and Loss, we are more happy. So that's partially because the idealized group model seems to be reliable. If we really have an attacker that, at least on elliptic curves, really takes some advantage on the bit representation, this may be considered a breakthrough. So such idealized group seems to be reliable. So the meaning of does and runs research, first you can consider as of theoretical interest, maybe some kind of existence problems in different idealized model. In the practical side, you can consider it as a backup of the simple BLS in case that there is really a breakthrough to make the idealized group not reliable. Maybe it's meaningful to switch to does and runs protocol. However, I would say this may be really unlikely. What about the story of Schnorr? So this line, initiated by Komlo and Goldberg, they propose an efficient special Schnorr protocol Frost in the modern setting. Again, it is only proof in static model. For adaptive security, we don't know. No proof and no attack. After that, Kreis, Komlo, and Moller propose a new special Schnorr scheme that is slightly less efficient than Frost, but they prove adaptive security for this. And roughly speaking, this result is like Bartram and Loss result. This says that Sparkle is secure with idealized group. This is an awarded paper in Crypto 2023. At the end of their talk, they say that the same result and similar proofs for Frost are coming soon. So following Sparkle, there is a line of research trying to avoid the idealized group. Some construct non-Schnorr special scheme. Some construct Schnorr special scheme. However, none of them are as efficient as Frost. So somehow this line has not been closed. But again, looking back, given if we really have the same security result for Frost as Sparkle, then practitioners should be happy to implement Frost in practice in the real world. So again, all the following work, they can be considered of theoretical interest and to be a very unlikely backup of Frost. However, there is a strange thing that the proof of frost never came out until very recently. It was shown that, yes, we do have the same security result for frost and sparkle, but the original result for sparkle was flawed. So in the recent work, Christ, Katz, Komlo, Tesaro, and Zhu show that you cannot prove the security of frost and sparkle without assuming a new assumption called LDVR. And this assumption, what I think interesting is that this assumption is not related to cyclic group. So I think similar, it should be an independent hardening assumption other than the idealized group. So this problem is new and less and not that well studied. I would say this may put a question on whether we are happy to implement frost, because this introduced another point of failure. So this new progress actually strengthened the backup meaning of the line of research following Sparkle. So what I think interesting about this story is that initially this research are motivated by removing the idealized group. Only recently it turns out that they also avoid the LDVR assumption by the way. However, I think this may be even more important. Okay, so now we are ready to go into a more technical part. In the first part, I want to show you about the proof and attack, actually mainly the attack, the LDVR attack on Frost. So I will start from a recall of Schnorr signature. Schnorr signature works over a cyclic group of prime order P with generator G. So in the key generation, a secret key is a random scalar, and the public key is G to the X. To sign a message, we generate secret randomness R, compute what we call a nonce big R as G to the R, hash the public key, the message, and the nonce to get a challenge C. Then we compute what we call a response Z as R plus CX. The signature consists of the nonce R and the response Z. And basically, a Schnorr signature is a proof of knowledge of the secret key small x. To verify the signature, we just check the equation G to the Z equal to R times X to the C. So Schnorr signature is very special friendly because look at here. What we do on the secret randomness R and X is just to compute a linear combination. So if we have additive shares of the secret value, then we should then the user should be able to compute additive shares of the response Z. This is the rough idea. The idea is we use Shamir secret sharing to share the secret key X, where we sample a random polynomial, t-degree polynomial. The main secret key would be a of 0, and the secret key shares will be a to the 1, a of 1 to an. With Shamir secret sharing, then for any subset of psi t plus 1, the secret key shares multiplied by a reconstruction coefficient, they are additive shares of the main secret key X. In the signing protocol, we let the user generate their own secret randomness as the additive shares of R. Then they can generate their own response as the additive shares of Z. So concretely, in Frost, the each user generate two partial nonces, RK and SK. So it turns out that they cannot generate the nonce in the more easy way that they only generate one nonce G to the R. If you do so, then this scheme turned out to be insecure. So these two partial nonces are combined in some way such that each user still knows the additive share of R as RK plus B times SK. So they can locally compute ZK in the second round, and in the third round, not in the third round, and after the second round, the individual responses will be combined into the final response. This is how frost work.
So what do you count as the first round? The secret sharing of X?
Yes. Although you don't need to use it actually. In the
Uh,
first round, you just do this. You just locally sample randomness
yeah,
and
so
output the nonce.
I wouldn't. Maybe it's a issue of terminology. When you say round, you also count the local computation as one round.
Yeah. So in one round, each user locally computes something and broadcasts the output of this round. So in the first round will be each user generate the partial nonces and broadcast RK and SK. In the second round, each user will get others RK and SK, so they can combine them into the combined nonce R. Yeah. So here we can see two advantages of frost. First, the first round is independent of the message mu and even the set of users S. So the first round can be preprocessed offline. Each user can locally run the first round many times, propose many partial nonce. Then this user will get prepared for online signing for many messages in one round, right?
So your offline phase is reusable?
Not reusable, but you can just concurrently do it many times. You just run many preprocessed rounds.
I see. All of these hashes are random.
Yes. And a second advantage is that there is a really straightforward identifiable abort because what each user output in the protocol is basically a Schnorr signature, the RK-SK and the response ZK. These are verified under the public key share XK, which is just G to the XK, G to the small xk here. So if a malicious user output something such that the combined signature is not valid, then what is output must not pass this verification. So the malicious user will be catched. I want to skip something here. I want to skip about the proof of frost in random oracle model and AGM. I want to mainly talk about the attack. So basically here to handle adaptive corruptions, we let the security reduction to assume an interactive assumption called the one more discrete log, where we are asked to solve T+1 discrete logs using T queries to a discrete log oracle. So when the adversary make corruption query, the reduction also make an D-log query to get the secret key it does not know. But there is a problem in the proof in the random oracle model because the reduction use rewinding. So we actually need to run the adversary twice. This means that using the T cost to the D-log oracle, we can only handle T over 2 corruption queries in each execution. So In the random oracle model, we can only prove a half adaptive security, where half of the corruption is adaptive, the other half has to be static. So the proof for full adaptive security assume an idealized model called the algebraic group model. And roughly, this model allows us to do straight line extraction of discrete logs. So we have a reduction, only run the adversary once. So now, however, this proof is not that straightforward because we need to handle so-called an attack in the proof. So I will go to the attack. So
Is this what you call something like LEVR attack?
yes, the
so that means this attack is real. So the previous security proof has a bug.
Yes, the previous security proof has a bug, but I had to say that I call it an attack, but it's not really. So actually, there is a step that we don't know if we can efficiently do.
I see.
But to prove it, we need an hardness assumption. So to prepare for this attack, recall that the secret key share xi is the polynomial a evaluated at point I. In the attacker sees the public key shares and the main public key x, x1 to xn. From this group element, it can compute group element a0 to at, whose unknown discrete log are the coefficients of the polynomial. When the attacker corrupts user I, it gets this inner product. I call the first vector vi, and the second vector a is the coefficient vector of the polynomial a. So this is just the polynomial evaluated at point I. Now we are prepared. So the attacker generates a nonce as a random linear combination of group element A1 to AT. It hash everything to get a challenge. Now to forge a Schnorr signature, what we need is just to find Z, the discrete log of R times X to the C, which is the discrete log of A0 to the C because A0 is just X, the main public key. A0 to the C, A1 to the beta 1, AT to the beta T. I write it in this way, where the first vector consists of C and beta 1 to beta T. I call it U, marked inner product by A. So we can indeed find this discrete log if we can find a corruption set C, such that the vector Vi defined here, Vi for I in the corruption set, span the vector U. Because here, if this vector can indeed span them, then we can efficiently find the coefficients. I call the coefficient Vi. If the target vector U equals to the combination of Vi, then the discrete log we want to find, U in the product with A, is just a linear combination of the secret key shares we get from the corruption queries, right? So this is how the attack works. The key step that we don't know how to do is finding the corruption set that span this vector. So this problem can be stated in a way that, without talking about the group, the authors call this problem low-dimensional vector representation. We have an oracle where we submit beta 1 to beta t, and the oracle sends us the first component, beta 0. The goal is to find a corruption set such that Vi for I in C span the beta vector for some oracle query. So we can make many oracle calls until we find a beta vector that we know how to span. So here we want to, here we only have T corruptions. So in this problem, we want to find T in linearly independent vectors to span a T plus 1 dimensional vector. So this is why this problem is called low dimensional representation. And in total, we have n choose T ways to choose the corruption set, right? So when n choose T is large compared to the prime order P, statistically, there should be guarantee a solution, should be guarantee a corruption set. However, computationally, it's not clear how to do so. So this problem is stated without mentioning cyclic group. So it's another, it's an actual hardening assumption not in the discrete log family. Any algorithm of small o of square root of p will give an attack better than solving discrete log. So if this is true, then maybe this will affect the parameter choice of the scheme. So far, for 128-bit security, we are happy with 256-bit group. But if we have a better attack, then maybe we need to choose another group. In practical, it is very undesirable. So to summarize this recent work, the authors, assuming OMDL and LDVR, they prove the security of Frost. And it turns out that LDVR is necessary for the security of Frost. This is what I want to talk about, the attack.
So it's unclear to me what's the goal for beta 0. I know that it comes from the fact that you are using random oracle to compute the hash in the construction, roughly because of that. Yep. But does it contribute to the hardness of this problem? It seems this problem hard even if you don't talk about beta 0.
Yeah, so here, beta 1 to beta t is the attacker can choose. So if the attacker can choose all the t component, all the t plus 1 components, then it must know how to span it. So here, the attacker only choose t components, but one component he cannot control. So this seems make it hard to span it.
Okay. So this beta 0 is really the source of hardness.
Yes. Yeah, so in the last part, I want to talk about 3 approaches to give new construction of adaptively execute special signatures. The first approach, I call it BLS approach. The main idea is that recall that Barton and Lotz prove adaptive security of simple BLS, and the LDVR attack does not affect it. So the BLS approach constructs not standard Schnorr not threshold Schnorr, but a friend of Schnorr, CP signature by Trump Patterson. It can be explained as a pairing-free implementation of BLS, although it is proposed earlier than BLS. So the signature consists of a BLS signature plus a Schnorr-like proof of validity of the BLS signature. So this proof allows the verifier to verify BLS without using pairing. So following this approach, Barchow, Lotz, Tesaro, Wagner, and Zhu proposed a 3-round special CP signature without assuming AGM. However, they still use some kind of one more assumption, but they have a very clever variant without the one more assumption. So from standard assumption in standard model, except ROM. And in one of my recent work, I showed that we can actually do the most stupid thing we just cut off one round from Twinkle and everything is still secure. So I directly get a 2-round scheme, and other result is the same as Twinkle. This is the first BLS approach. The second approach, I call it masking approach. So recall that to prepare for the attack, we say the public share is known to the attacker, and the attacker used them to compute the group element A0 to AT. So the idea of masking is to let the protocol never reveal the public key share x1 to xn, which is g to the small x1 xn. We cannot just say in the key generation we do not output them, because if the signature still verify under the public key share, then the signature will leak information of the public key shares. So in this approach, the idea is to mask the signature using one-time shares of 0. So now pretend the signature is homomorphic and non-interactive aggregatable. We let the masking signature be sigma I plus delta I, the one-time share. When we combine the mask signature, the one-time shares, because they are shares of 0, they are cancelled out and we get the original combined signature. The result is that the only information an attacker can get is combined signature under the public key. No information about the secret key shares is leaked in the protocol. So this masking approach actually allows us to equivocate the secret key shares. That is, in the security proof, when the attacker corrupts a user, we just uniformly sample secret key shares. And how to generate the one-time masks? It turns out that if we let each pair of users share a symmetric key, then they can generate a one-time mask in a smart way by hashing the symmetric key and something that they agree on. This must be a common input for them. However, so far we pretend that the signature is homomorphic and non-interactive aggregatable. However, for Schnorr, we use an interactive protocol where the two components of signature shares generated in different rounds. So it turns out that both of them need to be masked, because the nonce is similar to the public key, right? So you need, when you are corrupt, you need to output your secret randomness. In the proof, we also need to equivocate the secret randomness. So we also need to mask the nonce. When we mask the response, we are happy because we have a common input that is the transcript so far. But when masking the nonce, it is at the right beginning of the protocol and we have nothing common for the users. They don't have any consensus. So we have to have one additional round to gently sample some randomness as an input to get the mask. So following this approach, Katsumata, Ridgely, and Takamule mask a 3-round sparkle and get a 5-round scheme. So in addition to this one extra round for masking the nonce, they also need another extra round for some technical reason. And in another recent work of mine, I follow this approach to mask frost, and the only cost is the one extra round to mask the nonce. I get a 3-round protocol. I also mask a strand of Schnorr. It's not a standard Schnorr signature, but somehow it's more masking friendly in the case that the nonce does not need to be masked. And the main disadvantage of the masking approach is that now the signature share becomes unverifiable. So we don't have the simple identifiable board anymore. We either need to use some NIST proof to prove correct evaluation of the signature algorithm, or in a recent work, the author proposed an interactive identifiable board protocol. The last approach, I call it verifiable masking. Sounds a bit controversial. So I don't know how to talk about it in a high level. So I need to go concrete. Here, the secret key shares are shared of x, 0, and 0. And the public key shares are still g to the x. The public key shares, they are generated in a somehow masked way. We do not directly public g to the xi. Instead, we public g to the xi times h to the yi times u to the wi. In the signing protocol, we do the similar thing for the nonce. We mask g to the r by something to the yk times something to the wk. And to know that here, because y and w, they are shares of 0, so somehow the public key shares and the nonce, they are also masked by shares of 0. So when combining them, everything is cancelled. The good thing is that now the signature share is verified, it satisfies some relation under the public key shares. This relation is not directly verifiable because y and w is secret, but it can be easily proved using a Schnorr-like proof. This so-called masking technique is different from the previous approach. It does not allow us to equivocate the secret key shares. So in the, well, actually because here also yi, wi, they are shares of 0, but they are not one time. Only the group element here are one time. So something get different. But it turns out that assuming DDH in the security reduction, we can, well, carefully simulate an indistinguishable game. So I have to skip the things here. So let me skip the details about the security here. Just state the result. Following this verifiable masking approach, the best we can do so far is 3 rounds. And it's because in the security proof, somehow we need a committing round at the very beginning of the protocol to let the reduction to extract the randomness of the adversary. And we don't know how to remove this.
You call this verifiable masking. Why verifiable is the
Yeah.
IA?
Yes, for IA. So the
So I'm wondering, in the previous masking technique, you are saying that one is not desirable because to verify you need to run something like heavy and easy.
Yes.
But here, like, as you said, you still need to run more like easy.
Yes, so here it is different because the previous masking approach, the NIST should contain correct evaluation of cryptographic hash, something like this. Here it's only a simple algebraic statement, so the proof will be very simple. Yeah. So the last thing I want to mention is what I found interesting after this recent progress. So basically, previous work built backup for frost, focus on avoiding the idealized group. And by the way, they also avoid the LDVR. However, none of them are as good as Frost, like I said. Dasso is good like in other places, but it's not a standard Schnorr. The best special Schnorr without AGM is 3 round, not 2 round. So after this recent progress, that is the LDVR attack, I would say that it would be a meaningful backup. Even if we embrace AGM, we only avoid LDVR. So the last line is what I'm interested in. Now we allow the AGM. Can we build a special Schnorr in 2 rounds with efficient identifiable board and adaptive security?
Well, why do you prefer algebraic group model over LDB?
Yes, like I say, the idealized group seems to be reliable, and this group stuff is like rather well studied. So yeah, but also another interesting open problem is of course the hardness of LDVR. Any reduction or attack will be interesting. Yes, this is all of my talk. Thank you.
Excellent. Any questions? Okay. Okay. Then thank you for the talk. Yeah.
Yeah.
And thank you
Thank you for
everyone
listening.
for joining us.